Welcome back to Cyber in Practice. I'm Lewis Knox, and in today's episode, we're taking a look at non-repudiation and digital signatures. We'll walk through how digital signatures help verify identity, protect integrity, and detect unauthorized changes to data. So, what exactly is non-repudiation? At a high level, it means a sender can't deny creating or sending a message or a file. In cybersecurity, that's important because organizations need a reliable way to prove where information came from and whether it can be trusted. Digital signatures help support this by verifying message origin, preventing denial of authorship, and helping establish accountability. Digital signatures use cryptographic keys to validate both legitimacy and integrity. The private key is used to create the signature, and the public key is used to verify it. Because the signature is mathematically tied to the original data, even a small modification to the file will invalidate the signature. That's what makes digital signatures effective for detecting tampering. Signature verification confirms a message came from the expected sender and that contexts haven't changed. When verification succeeds, it helps establish trust in data. It confirms sender's identity, validates integrity, and helps detect unauthorized modification. One of the biggest advantages of digital signatures is tampering detection. If a signed file is modified after the signature is created, the verification process will fail. That failure immediately tells us that the integrity of the file has been compromised. This is a key security control used throughout cybersecurity to protect trusted communication and data. In this demonstration, I'll create a message file, digitally sign it using GPG, verify the signature, modify the signed file, then validate the signature verification failure after tampering occurs. For this demonstration, I'll be working inside an isolated virtual lab environment using Kali Linux, GPG, the Linux terminal, and Nanotext editor. I already have the project workspace prepared, so I'll move into the directory and walk through the sign-in process. Here, I'm opening a text file that will be used for the digital signature demonstration. As you can see, we have a simple policy approval message, approve security policy change. I'll save the file and exit editor. Here's the original file before it's digitally signed. Now I'm using GPG to digitally sign my file. This creates a cryptographic signature tied to my private key, helping verify legitimacy and integrity. Now let's view the message again. We will now be able to see the signed version of the message along with an embedded digital signature block. This signature is what allows systems to verify whether the file has been altered after signing. With the file being signed, the next step is verification. The verification succeeds successfully. This confirms the message originated from the expected sender and that the contents have not been changed since the signature was created. But what happens if someone modifies the file after it's been signed? To simulate tampering, I'm going to modify the signed content. I will change the word approved to denied and save the file. Now that the file has been altered, let's verify the signature again. And now the verification fails. Even though only a single word was modified, the digital signature no longer matches the original data. That failure immediately tells us the integrity of the file has been compromised and that context can no longer be trusted. So to wrap everything up, we saw how digital signatures support non-repudiation by helping verify legitimacy and protect integrity. We also demonstrated how modifying a signed file immediately invalidates the signature verification process. This same concept is widely used in secure communications, software validation, identity verification, and many other areas in cybersecurity.
Thank you for watching Cyber in Practice. If you enjoyed this demonstration, stay tuned for future Cyber in Practice episodes.